Well friends, now we have another interesting optical device and that is about prisms. Prism is a transparent material made up of glass, and as you can see, this is a prism. A prism consists of the section is a triangular section. You can see it has a triangular section. It has got one rectangular face, another rectangular face, and third, that is a rectangular base. So in total, a prism has 6 faces: 1, 2, that is 3, 4, and 5. Sorry, 5 faces. And a prism is used in optical science or optical instruments for separating white light into its constituent colors. We have seen in our last lectures that white light consists of a mixture of all the monochromatic rays, right from violet to red. Vibgyor, you know those Vibgyor, the 7 colors, the basic colors. Now these colors are mixed in normal white light. So in the everyday life, wherever you see the light of tube light, the rays from the sun, then consist of the mixture of these 7 colors. Now it is only through a device like this prism, when it is in white light is incident on one of the rectangular face, then from the other face the separated colors can be seen. I will show you a small video on actually how when the white light is incident on one of the face, how the prism sends that white light into its constituent colors. Now what is the importance of prism as in the study of optics? Through the help of prism, instruments which are used in chemical analysis of gases, spectrometers are used. It is with a spectrometer that various light, when it is made to pass through various gases, so different gases will absorb some of the what we call constituent chromatic rays, and the ones which they allow to pass through that, they do not contain a particular color. Say for example, if I pass the white light on a gas such as hydrogen, so it might absorb yellow color. So the output colors are all the colors except yellow. Still they will look like white light, because one yellow color missing is not going to change the color of white light. Now how to know which color is? So when this ray which has passed through the gas, it is made to fall on the prism, it will separate into constituent colors. You can see one yellow color is missing. Now which is the characteristic behavior, suppose for example I am giving of a hydrogen gas. So this is the way how are able to identify which type of a gas it is. Right? So just see the small demo. Here you can see that a white light is incident on the prism, and how the separated colors are the separated colors are taken on a screen, that's on a white paper. You can see the formation of Vibgyor. Of course, a more better prism able to separate it more precisely, more accurately. So it depends upon the quality of the glass that is used that you will be able to see this dispersion.
This is an example of a prism being used as a spectrograph, words used to separate colors. The prism is the triangular object in the middle, made out of glass. From the bottom left, you see the incident beam of light, which is white light, and towards the top, it's partially reflected. But within the prism, the white light is refracted, and then when it hits the surface to the right of the prism, it's refracted and dispersed at the same time.
So this is a phenomena of white light which falls on a prism. Now after this, this is one of the applications, use of a prism, and for making its use for different what we call optical instruments, usually the ray of light, how it passes through that, and what are the various different angles of the emergence, incidence, and angle of prism plays an important role in defining the dispersion power. That is what we are going to see in the next lecture. Now in this following lecture, you see, just we are going to study about prism and all the equations related to that, but we are going to use only one monochromatic ray. The same property, as I have said, will be followed for all the other monochromatic rays, but we cannot draw all the rays in a diagram. So now here we are going to only one particular ray, and then we are going to see how it behaves when it passes through a prism. Well, now look at this. I have drawn a prism. Now this is the rectangular section of a prism, sorry, triangular section of a prism, and the prism is in this way. I have just shown you that this is how we have drawn the prism of the triangle. This is a rectangular face on which the ray is incident. Now here when we study, we have to consider a ray. So let us say a ray is incident here. Though I have shown this as a blue color because I have taken one monochromatic ray. But if this was a white ray, it would have got dispersed into various different colors. There would have been an angular dispersion. Now this monochromatic ray, when it is incident, the angle of incidence is called as R. Before that, we say if this is a triangle, this angle A is called as angle of prism. Correct. Now this prism is made up of glass material, and it will have some refractive index. So this is the refractive index of this glass, which is given as mu, which is the refractive index of this. Now, as you see that it is incident on this, say, point O, so definitely it will get refracted inside this material, and this is going to be the angle of refraction, say R1. This is going to be the angle of refraction R1. This refracted ray at this point at say maybe N. So at N, after striking, it is again going to get refracted back into the air. Now this time, this is, suppose say the angle of incidence, let me give this as R2, right? Then this would be the angle of emergence E. E is called the angle at which the ray is emerging from the prism. These are the angles how we have to take. This is the angle of incidence, and this is the angle of emergence, which means a ray which is striking here at this position or this angle ultimately comes out at an angle of emergence, that is E. Now this ray, if the prism was not there, it would have gone straight in this particular direction. Now because this prism was there, this ray got deviated in this direction. So now this is the new direction of the ray. So I can say that if I extend it backwards, this angle can be described as angle of. What does this mean? Angle of deviation means this particular ray, which would have gone straight, because of the prism got deviated by. Is this clear? So this angle is called as angle of deviation. Now how much a ray is going to deviate? It depends upon this, that is the angle of prism, angle of incidence, and angle of emergence. So all these variables are related by this simple equation, which is given as I plus E is equal to A plus D, where I is your angle of incidence, E is your angle of emergence, A is the prism angle, and delta is the angle deviation. So this is how the variables are related as far as a prism is concerned. So this is a basic prism, and these are the basic relations which to a prism. Right? Please draw this diagram and try to understand all the variables and the angles as mentioned in this diagram. Okay. Now there is another relation that we have to see, and that is the relation of angle of and the angle of deviation. Here there is a very unique relation between the angle of incidence and the angle of deviation. The unique relation is that, suppose, say for example, the angle of incidence will start at angle 0. Angle 0 means which will be perpendicular to the or normal to this particular face of the prism. Suppose I show this as the ray of light which is being incident. So what are the different angles I can have? It can start from angle 0 and it can go from angle 0 to angle 90. This ray can have, these are the probable angles this particular incident ray can have. So let us assume that it is starting from 0, which the angle of deviation, now let us consider this as the angle of deviation, correct? Now let us assume that initially this is the angle of deviation, this is the position. Now as I increase my angle of deviation, angle of incidence, I keep on increasing, the angle of deviation keeps becoming, it starts reducing. It starts reducing, this is the angle of deviation. Here angle of incidence I am increasing. After one particular angle of incidence, there is one particular angle of incidence, after which even though I keep on increasing, angle of deviation will not decrease further, but again it will start increasing. As you can see, as I keep increasing, it again keeps on increasing. If I reduce this, again it will keep going, it will keep decreasing, the angle of deviation is decreasing, right? And it will go to a minimum angle of deviation, and if I further decrease my angle of incidence, the angle of deviation will again start increasing. So what do we is that for an increasing angle of incidence, the angle of deviation starts reducing. It goes to a minimum value which is called as delta m, that is a minimum angle of deviation of a prism, which is defined for different prisms. And after that, when you further increase the angle of incidence, the angle of deviation starts increasing, which means there would be two angle of deviations for two different angle of incidence. Let us see a form of a graph, right? So now I am going to draw a graph for this angle of incidence and the angle of deviation. Okay, now you can see this graph shows on the x-axis, that is angle of incidence. That is, this is the angle I which is being shown, which will vary from 0 to 90. For different angle of incidences, different angle of deviation, like suppose this is D1 for I1. Later on this I1 increases to I2, D1 reduces to D2. Then here when it is I, this becomes the minimum deviation, so it is called as delta M. After that I is again increased to maybe I3, so for which again it will have a deviation I2. Then again maybe slowly when it is increased to I4, it will have the same deviation delta 1. So from this graph you can come to know that for two angle of incidence, that is I2 and I3, it has same angle of deviation delta 2. Again these are the two samples I1 and I4, it again has the same angle of deviation, that is delta 1. So for so there may be various different sets of two sets of angle of incidences for which you will get a single deviation. Similarly, okay, so from that you can infer that there is one angle of incidence which I have written here, only I. So this is the only angle of incidence I, for which you have only one angle of deviation, and that is the minimum angle of deviation. The ray will not below this particular angle of deviation, and therefore this is the condition that is obtained when angle of incidence is equal to angle of this. It is a very important equation from problems point of view, which gives a relation of I and E, and this is the time when it is delta m, that is the angle of deviation, becomes delta m. The equations becomes this way, that I plus E equal to A plus, say, delta. When delta is equal to delta m, I is equal to E, so you can be written as 2 into A plus delta m, or 2E is equal to A plus delta m. These are the various relations that you at the minimum angle of deviation when you will be solving the problems. Now, with this particular part, there is an equation that relates the refractive index of a prism with the minimum deviation, and that equation is given as the refractive index is to sine of A plus delta m upon 2 upon A upon 2. This is the relation of refractive index of the glass, prism angle A, and the minimum deviation delta m. Is this clear? This can have an extended equation. Now this is the refractive index of glass. So there are some problems which are asked where they will ask you that if a prism is kept in water, or if a prism is kept in some other media other than air, and certain value, and then they will ask you what will be the angle of prism or the angle of deviation. So that time the same formula has to be modified as refractive glass of the prism upon refractive index of the medium in which the prism is kept, and after that this same formula will be. So you should know how and when the refractive index of the medium is used. Wherever there is a mention of refractive index, you should assume that it is the refractive index of medium, because if this refractive index is air, the refractive index of that medium is going to be 1, and that formula gets applicable. Please make a note of this.
This video demonstrates the angle of minimum deviation of laser light passing through a prism. So what I have set up here, beam of laser light, and you can see the path that it would take if there was no prism in the way. When I do put the prism in the way, however, you see that the laser light that was passing over the top of the prism still comes over here, but the piece that actually passed through the glass ends up being way over here. So the angle between where the light would have gone and where it is going now, having passed through that prism, is called the angle of deviation. One thing that's interesting is that the amount that the light gets deviated over here changes depending on prism face at. So by changing the position of the prism, we can make this angle of deviation bigger or smaller. So I'm going to do this now. I've got this prism mounted on a rotating platter, and I'm going to move this back and forth and show you what happens to that angle of deviation. So if I turn the prism in this direction, you're going to see that spot of light get farther away. In other words, the angle that the light is deviated by get larger. So let me demonstrate. I turn it this way, and that spot gets farther away. If I turn it back the other way, you're going to see something interesting. It comes closer, and then it turns around and starts heading out again. So there is a minimum angle of deviation, that point where the spot of light changes direction. And if you go too far in either direction, that beam of light gets farther away rather than closer. So that angle is called the angle of minimum deviation, because the angle between where the light was supposed to go and where it did go is at its minimum. So let's have a look at this. So here you can see my prism, and I am going to move my light source so that you can see the beams a little bit better. So now you can see the beam going into the prism, through the prism, and also exiting the prism. Now if I move this back and forth a little bit, you can see what the side the prism is doing. The angle of minimum deviation takes place here, and you might notice that things look pretty symmetric in this situation. The beam in the prism is going straight across, parallel to this far face. If I turn the prism in one direction, it's no longer parallel. If I turn it in the other direction, it's again no longer parallel. Minimum deviation takes place when it is parallel. In other words, when the beam inside the glass is at 90 degrees relative to the plane between the two faces.
Yeah. Now, this is one more different type of prism which is called as a thin prism. This is a thin prism. As you can see, the angle A, that is the prism angle A, is very small, approximately to the tune of say 18 degrees and below. So if the prism angle is somewhere less, 15 degrees, 18 degrees, 10 degrees, then this kind of prisms are called as thin prisms. Now these thin prisms are not effective and used for dispersion of light. There are certain other applications which are used with prisms that we will just see in the following sessions. But right now, let us try to understand a thin prism. Now in this thin prism, we can use the same equation that we use. It would also have some refractive index mu. Making use of this refractive index, we have our equation that mu was equal to sine A plus delta m upon 2 divided by sine A by 2. This is whole one complete angle. Now we have, in physics, we have the liberty to do certain approximations, otherwise the equations will keep on being and it will go into a very mathematical expressions which should be very difficult for us to solve. And the basic intention of understanding the phenomena, that would be different and one would go into the details of the mathematical representations. So here we are going to take certain approximations. Now one of those approximations are that whenever a theta of an angle is very small, then sine theta will tend towards the basic value of theta. So sine theta becomes theta, tan theta beta, and cos theta, as the value of theta becomes is very small. So for cos theta, when the theta is very small, that is what is the smallest angle, that is 0. So cos 0 becomes 1. So for small angles of theta, sine theta becomes theta, tan theta becomes theta, and cos theta becomes 1. So here, since we are bothered about sine theta, so it comes to mu equal to sine theta, we can be written as 1 plus delta m upon 2 divided by. So you can see from here, I can cancel this 2 and this 2, okay, because they are in the denominators of both the expressions, and this mu can be written as a plus delta m upon a. On further simplifying this, you get mu a is equal to a plus delta m, and delta m can be written as mu a, and therefore a mu minus 1, that is your equation of delta m. So this equation of delta m will be applicable, please remember, only when it is a thin prism. If it is a normal fat prism having an angle 30, 60, then minimum deviation, this particular relation, minimum deviation will be there even for a thicker prism, but this relation delta m is equal to a mu minus 1 will not be applicable. Now there is one more important aspect that I would like to tell you, that we had seen from the start that for different rays the refractive indexes are different. So similarly for different monochromatic rays. So different monochromatic rays will also have different angle of deviation. So it is written in this particular manner that this can be written as delta m for red is equal to a mu of red minus 1. So this is the equation which represents delta r. Now we don't have to keep writing delta m because it is understood that this equation is for minimum deviation. But this minimum red color, because red color will take up or deviate depending upon the value of refractive index of red. Similarly, deviation yellow will be given as mu of yellow minus 1. Deviation of violet can be written as a, and refractive index of violet minus. So I am not writing all the 7 colors. Normally there is a tendency or a practice of writing only these 3 colors, because these 2 are the extreme colors and y is the mean color. That is where it has the deviation is between them. Numerically, y does not fall the center of r and y. It is just taken on the basis of deviation, that y is considered as a mean deviation. There are different deviations which will be produced by a prism in this particular equation. Please. Yeah. Now we have this the diagram drawn again. So here I have shown there is a white light that is incident on one face of the prism, and definitely it gets dispersed into constituent colors starting from red to blue. That is your vitriol. Violet is never used. We always talk with blue color. That is, blue is more visible to our eyes rather than violet. So the violet is there, but blue is more prominently seen. That is why we see we take the extreme color as the blue color and this as red color. As you can see, the deviation of red is the least. Deviation of violet is more. Now, this is also one of the reasons which you must have done in your 9th and the 10th standard, why the sky appears to be blue. That is because the blue color deviates more, and therefore the effect is seen more vastly with the blue color. And whereas why are signals using SOS or a danger signal of red color? Because red deviates the least, and therefore it will pass directly and straight, and it will be visible to a human, to danger signals. So these are the various signals various light rays which have been dispersed from this particular prism. The prisms will have this particular angular dispersion. This is the angle between the red and the blue. Now angle, how much the angle is more, so the quality of the prism is judged upon how much the rays are being dispersed. So this certain entity of physics which measures how much light separated, how much the constituent colors can be separated. And for that we are going to make use of the equation, that is the dispersion, angular dispersion of this red and violet, because these are the two extremes. By how much angle they are separated, that is what we are going to see over here. So from this equation, this is a very generalized equation, any ray, if I apply this for deviation of red, it will be written as mu of red minus 1. Deviation of violet can be written as a mu of violet minus 1. So this is the deviation, as you can see, this is the angle of deviation of red, and this is the angle of deviation of red, and this is the angle of deviation of violet. Okay. So what is the angle between red and blue? So that will be deviation minus deviation of red. So if you subtract this equation, you will get a mu of violet minus mu of red. So this expression is called as angular dispersion. That is at how much angle the red and the blue are separated from each other. More the separation, more it is better, because the use of prism depends upon how much it can separate constituent colors. Now there is a measure, or there is an unit entity known as this omega, which gives you the dispersive power. This is called as dispersive power, and this is given as angular dispersion upon the mean deviation. So this is called angular deviation or angular dispersion, that is dV minus dr upon d. We take yellow as our mean deviation. Deviation of yellow is mean as compared to violet and red. If you see from yellow exactly in the center of this tree. As I have said, we are not taking yellow as from the pattern or the arrangement of colors, but this mean deviation, mean of the deviation of violet and red. If I take the deviation of, or if I take the mean of violet and red and divide it by 2, I will get dy. So many times in the problems, dy is not given to you, and they expect you to find the dispersive power. So dy can be substituted or can be rewritten as dv plus dr upon 2. So what we have taken the mean deviation of violet and red. So here the dispersive power of a prism is given. Now this is an arrangement of two thin prisms. Now both the prisms are made of different material. Maybe this is made up of glass, this is made up of crown, or it could be some other material, but of course it has to be a transparent material. And let us consider this is having a refractive index as mu1, this is having a refractive index as mu2. Here the prism angle is given as A2, here the prism angle is given as A1. Right? So this is how they are different from each other. They are not made up of the same material. Now what is the importance of these two refractive prism? Here as you can see, when the white ray enters or strikes one of the surface of the prism, then it undergoes dispersion into its constituent colors. Then there is another prism which is kept with the two faces touching each other. Here again the dispersion takes place, and ultimately they get again joined into a white ray. So a white ray comes exactly as a white ray. So here what have we achieved? We have not achieved any dispersion, we are not able to see any colors, but there is one more important thing seen, that in this particular case we had achieved a deviation of this ray at an angle. This white ray could deviate at a particular angle delta. Now this angle delta, that is called as, I am trying to bend the ray of light. Many things where you need to change the direction of the light as per our convenience for certain optical instruments. Now in that particular, such combinations are used, that is an achromatic combinations of prism. This is called as achromatic combinations of prisms. Achromatic combination. Okay. So in this achromatic combination, as you can see, we have not achieved actually dispersion of light, but we are able to change the deviation of this light, and therefore this is also called as, it is called as deviation without dispersion. So this arrangement gives me a deviation. This ray would have gone straight, so I am able to deviate at a particular angle, but I am not expecting, now this is not used for seeing constituent colors, this is only for bending the straight what you call white line. And so I am going to fall on it, all the rays will be passing through this particular direction. So it is like changing my angle of sight, right? Certain, suppose if they are at a particular angle and I have to bend my neck to see that straight ray of light. So instead, such kind of is made, so it becomes easier for me to see at my eyesight by using this combination. So I am able to change or deviate the ray of light as per my convenience. Now this also has an equation. Now why does this deviation without dispersion takes place? Right? So there is an equation for that. How much ever angular dispersion this prism makes, the same angular dispersion the other prism has to make, only then it will get merged back into white. What is the angular dispersion for prism 1? As we had seen in the last session, it was deviation of violet minus deviation of red as a mu of violet minus mu of red. Now this is the angular deviation of this prism, which is given in this term. Now here I have to change, because the angle is A1 is the angle of prism. Now refractive index of violet of prism 1 and refractive index of red of prism 1. So this is the angular dispersion of prism 1. D V1 dr1. So d V2 minus d R2 will be A2 mu of V2 minus mu of R2, that is violet minus red. Now this one has to be equal to 2, that is the angular dispersion of prism 1 has to be equal to the angular dispersion of prism 2, only then they are what you call diverging, and later on they are converging to the white ray, right? So equating 1 or 2, we get an equation that is mu V1 minus mu R1 equal to mu V2 minus mu R2. So this equation is an equation for achromatic combinations of prisms which are used in the combination. As I've said, it could be flint, it could be crown, it could be glass, it could be different material and the different angles. So you have the angles and the refractive index to get the deviation of your choice. Now look at this arrangement that is shown. Again we are using the same similar kind of an arrangement as we saw in the last session, in which we are using again prisms in that achromatic combination, and in that particular prism we did not achieve any dispersion. It was just the white light and we achieved a deviation of that particular. Now this is an arrangement which is given as topic is inversion. As you can see, it is converting or what we call splitting into constituent colors, but it is dispersion without deviation. Now whenever this topic is read, maybe you read in your textbooks or when you see it anywhere, it becomes a bit confusing to understand that how can you say that dispersion is there and deviation is not there. All the rays are getting deviated. Okay, then how is this topic relevant? Now this deviation is not with the red and the blue. Unless and until they deviate, they are not going to split into the constituent colors, right? So if you want to have dispersion, red and all the colors have to change their angle as they enter the refractive indexes. Then how can we say that this is an arrangement which is giving me dispersion but not deviation? Just have a proper look at this diagram. The white ray is incident in this direction. A white ray consists of all the colors, in which yellow is also a mean color which is included in this white ray. When it goes to two different dispersions to prism, you can see the direction of yellow has not changed. It is in the same direction as it was incident. Just imagine in this there is a yellow color and the yellow color is going straight. The mean color is not getting deviated. This without deviation is with reference to your color. It is to reference to your yellow ray, a yellow monochromatic ray. So it is the yellow ray which is not getting deviated, and hence this is called as dispersion without deviation. Now you will keep wondering that why do we do all these things? What is the application of this putting these arrangements and trying to get this dispersion and no deviation? What have we achieved? Prism was also giving me dispersion, but it was getting deviated. Well, as I told you in my first lecture of prisms, that prisms basically are used used in a spectrometer. A spectrometer is a spectrum meter which is totally dependent on the observation colors which are in the mixed form, because the naked eye cannot distinguish which colors are absent and which colors are present. Only after passing through a prism we are able to see its constituent colors, and so then that is why they are called as that is why the instrument spectrometer, which is very widely used in the chemical laboratories. Okay, the basic application is in the chemical laboratories, and of course also checking the radiations from the sun and trying to see which rays are absent or present in them. Now a normal spectrometer, if I have to use using a prism like this, so how is it used? A ray of light is incident on it and the dispersion is coming in this particular manner, which is to be taken on a film. You have seen a video at the start of this session. I have shown an experiment in which a white ray is and the screen is kept at a particular angle, so that it was kept in this particular angle. If you remember, the screen was kept in this particular angle, and so the different colors visible on the screen. Now if I have to have a spectrometer, just imagine I am putting the ray over here and I have to bend my eyes to see the dispersion angle. The ray is coming over here and observing the dispersion in this angle, right? So it is inconvenient for an instrument. So instead, if a screen in the same direction in which the white color is incident, so my eyes are able to look at same direction. So it is used in the spectrometer, which is commonly known as a straight line spectrometer. So, and your screen and your eyes are all in the straight line. Here your eyes are going to be in this direction and the white ray is going to be in this direction. It's a bit inconvenient, and that is why these combinations are used to make it as a, or to use it like a straight line spectrometer. Now why does this behave in this particular way? Because here dispersion is taking place but deviation is not taking place. In physics phenomena, that whichever is explained ultimately has to be converted into an equation. So we cannot just keep looking at it and clap and say, oh well, good, nice things have happened. Everything, whatever is happening in physics should be brought in form of an equation, should be brought in form of mathematical expressions. So here what is being observed, the yellow color has not deviated from start and the emergent yellow color from the incident yellow color. So in between it, because when it passes, any color passes through a prism, deviation is going to take place. But it got deviated and it got re-deviated back to the same angle. So whatever deviation took place in this prism, the same deviation for the yellow color has taken place in the other prism. So in short, I can say the deviation of yellow prism is equal to the deviation of yellow color in the second prism. So let us give all these parameters. This is A1, this is A2, this mu1, and this is having mu2. So deviation of yellow color, what was the equation that we had used? That was A1, that is mu y1 minus 1 equal to A2 mu y2 minus 1. That will be how we are going to achieve this kind of an arrangement. That if I want to have a straight line spectrometer, I should be using two prisms having refractive index mu1 and mu2, having angle A1 and angle A2. Only then a straight line spectrometer arrangement can be achieved. Sometimes these equations, problems are asked from this particular equation. So please make a note and try to logically, don't try to by heart, try to derive this logically. So once you practice deriving logically, it will be easy for us to memorize. Remember, this is a basic psychology which one has to understand for memorizing. If this equation is directly given to you, and if I tell you that this is going to create a straight line spectrometer, it does not get registered in your mind. You should understand first what is a straight line spectrometer. Second, you should be able to derive the relations that you have been knowing, and then the brain accepts it and it makes it, keeps it permanent in your memory. So these are the techniques to read equations. You'll be giving your two exams, one which will be your board exams and second which will be an entrance exam. For an entrance exam, derivations is not necessary, but without derivation it will be difficult for you to memorize these equations. And for your boards, you will have to write down this in terms of, and you have to give a proper derivations for all these problems. Right? Please.